So this is question number 4. It's from the 2012 BC exam. It's a non-calculator free response question. And it's kind of an interesting problem. They ask us to estimate f of 1.4 in a variety of ways. So if you look at what we're presented with here, we're given this table of values. We have values of x and the corresponding values of f prime of x. The function f, we're told, has two derivatives for positive x's. We know f of 1. We know f prime of 1. And then we have the values from the table to utilize as well. Part A wants us to find the equation of the tangent line to the graph of f at 1, and then use that tangent line to approximate f of 1.4. So this is basically a tangent line estimation. So the slope of your tangent line is going to be your derivative at 1. You can steal that from the table. Your point of tangency is 1, 15. So here would be point slope form for the equation of that tangent line. You want to go ahead and estimate the y value on f by using the y value on the tangent line at the x of 1.4. So if you put 1.4 in place of this x right here and solve that equation for y by adding the 15 to the other side, you're going to arrive at your estimate for f of 1.4. In part B, they want us to use a midpoint Riemann sum, two subintervals equal in length, and these are going to be defined by the values that are given to us in the table, to estimate the value of this definite integral, and then we want to use that approximation to estimate the value of f of 1.4. Now this is a little sneaky. The Riemann sum is something that we've done quite a bit of. Estimating a function value after computing a Riemann sum is kind of new. But the Riemann sum, if you're taking the interval from 1 to 1.4 for f prime of x and cutting that into two pieces of equal width, is going to have our first interval range from 1 to 1.2 and our second interval range from 1.2 to 1.4. Now we want to do a midpoint Riemann sum. So the height of each of these rectangles is going to come from the value of our function at the midpoint of each subinterval. And I called it the function, but really we're doing this estimate for the definite integral with f prime as the integrand. But the midpoint of the first subinterval is 1.1. The function value, or the derivative value in this case at 1.1, is 10. So our first rectangle is going to have an area of 0.2 for the width and then 10 for the height. And then the second rectangle is going to utilize this for the height, because that would be the derivative value at the midpoint of that next subinterval. Do that calculation, you get 23/5. And then the tricky part of this question is, how do you use this result to estimate the value of f of 1.4? Now if you think about how you would normally compute the value of this definite integral, you'd use the fundamental theorem of calculus and you'd find the antiderivative of f prime. Well, the antiderivative of f prime is f. And then once you have that antiderivative, you're going to toss the upper limit in place of x, the lower limit in place of x, and take a difference. So when we do that, we're going to be looking at f of 1.4 minus f of 1. We know what f of 1 is. They tell us that f of 1 is 15. So the exact value of this definite integral is going to be whatever f of 1.4 is minus 15. We've approximated the value of the definite integral with this. So if we equate the exact value of the definite integral with the approximate value of it and then solve for the unknown in the exact value, solve for f of 1.4, we're going to have our estimate. So by doing that, we'd be trying to solve this equation. We would add the 15 to the 23/5, and that would give us an estimate of 19.6. When we check out part C, it wants us to do another estimate for f of 1.4. This time we're going to use Euler's method starting at 1 with two steps of equal size. So if you know the algorithm for Euler's method, you're going to generate your new y values by taking your previous y value, adding on the slope of the tangent line at your previous ordered pair, times whatever your step size is, whatever your distance between x values is. And so we know that this little table right here is going to go from 1 to 1.2 to 1.4 to get from this x to this x with two steps of equal size. We would first find our estimate for the y value that corresponds to the x of 1.2. So we would take the previous y value, which is 15. We would add to that the slope of the tangent line at the previous ordered pair. So the slope of the tangent line at 1 is going to be 8. And then our step size, the distance between consecutive x's, is 0.2. do the arithmetic and you get 16.6. And then you want to estimate what the y value is that corresponds to the x of 1.4. So you're just going one more round of Euler's method here, and you're going to begin with the previous y of 16.6. You're going to add on to that the slope of the tangent line at the previous y or at the previous ordered pair, and that would correspond to using 12 from the table. Delta x still 0.2, do the arithmetic, and you get 19 for your estimate of f of 1.4 using Euler's method. And then in the last piece of this, they want us to do one more estimate for f of 1.4, this time with a second degree Taylor polynomial for f based at 1. So if you know how to construct a Taylor series for the function f of x is going to be constructed using this formula, where we have the nth derivative evaluated at where the series is based over n factorial times x minus where the series is based raised to the n power. So I just applied that to the c value of 1. That's where we wanted this series to be based. And then I also am going till I see my second degree polynomial. So that would require me to go to my index value of 2. I then took f of 1 from here. Right, so 15 took the place of f of 1, 0 factorial is 1, something to 0 power is 1, so the first term's just a 15. F prime of 1 we can take from the table, that would be 8, divided by 1 factorial times x minus 1 to the first gives us this term, and then f double prime of 1 is 20, they gave us that, and then divided by 2 factorial, which is just 2, times x minus 1 to the second. So this would be your second degree Taylor polynomial for the function f. You want to use that to estimate f of 1.4. So you're going to put 1.4 into your Taylor polynomial, and if you do the arithmetic there, what you end up with is you end up with an estimate of 19.8 by utilizing that second degree Taylor polynomial. So like I said earlier, kind of an interesting question. You've got a bunch of different estimation techniques you're being asked to utilize in number 4 here, and they all give you values that are relatively close to f of 1.4.